Bend your ray down so it's just touching the edge of the rectangle. The next thing we have to do is we have to measure the angle of incidence. So to do that, how do we measure the angle of incidence? That's the first question. What does it have to be based on? Anybody know? Don't call out, please. Raise your hand. Mariano.
Isn't it the imaginary line that will be as straight exactly here?
Good, right? We have to base it from that imaginary line, and the name of that imaginary line is the cloud.
The normal line.
The normal line, right? So to make the normal line, we take our protractor, we place it at the point of contact on your surface. You rotate your protractor around so that the 90 is resting right on the line like that. Then you take your line, you want a dotted line for the normal line, and you're going to draw with your pencil a dotted line that goes right through that 90 degree, makes a 90 degree with your surface.
So now,
Yes, question?
no
No, it doesn't, because whether it's 90 degrees on this side or 90 degrees on that side, if you draw a line along the protractor edge, it's still going to form a 90 degree angle, right? So once we've got it set up, you reverse your protractor, and you get it set up so that it's all cross-haired on the intersection. Yes, Aline?
Just to make sure the normal line is always perpendicular to the surface.
Always perpendicular to the surface. It's located at the intersection point where the ray strikes the rectangle, right? So once you got that in, you got to measure the angle. So in this case, it's a little hard to read because it's a little big, but let's see if I can look. This is a 0, 10, 20, 30, 35, 30. It's like a 37 degree angle I've made here. So this is going to be our theta 1, right, is about 10, 20, 30, 35, 30. It's like 37 degrees in my case that I made up here. Right? The other thing you have to know is you have to know the two indexes, right? So in top, that's our N1. Our N1 is in air, so our index in air is 1.00. And in the diamond, that's going to be our second index because we're inside the diamond.
2.42.
2.42. Great, wonderful, we've got all that. Theta 1, theta 2. And the thing we're looking for, we're trying to find theta 2. We don't know theta 2. Theta 2s are, we don't know, right? So, right, when you got this and you're trying to find theta 2 for the refraction, we're going to use Snell's law, which says that N1 sine theta 1 is equal to N2 sine theta 2, right? So, N1 sine theta 1 equal to N2 sine theta 2. We just plug in our numbers. That's going to be 1 times the sine of 37 in my case. Is equal to N2, which is 2.42 times the sine of theta 2. Sine of 37, anybody have a calculator handy? Anybody? Mariano, I'll go with you. Make sure it's in degrees, not radians. Especially if you took calc this morning.
You said sine of what?
Sine of 37.
0.5299.
0.5299 is equal to 2.42 times the sine of theta 2. We want to get the 2.42 away from sine theta 2, so we divide both sides by 2.42. So 0.5299 divided by 2.42, Mariano?
0.21. Yeah, 0.21897. So
Just give me 4 digits. 2189.
0.2189.
Okay, 0.2189 is equal to sine of theta 2. And then to get theta 2, we're going to use sine inverse, right? To get rid of the sine, we go to sine to -1, sine to -1. Sine of -1 of 0.2189. 12.6, well, 13 degrees is equal to theta 2. The sine inverse cancels the sine. Right? Okay, great. So this is where we were last time, right?
Yeah.
Okay, now that we've got that, now we go to the part where we got to draw that angle. So, hey, quiet please. We're going to rotate you're going to rotate your protractor so it's on the far side of the line, like that. And then you're going to take a pencil and you're going to mark out 13 degrees on your protractor. It's easier if you make it a little bigger so it's easy to see. I'm just going to yours, this is about proportionally what it'll look like on yours. Your protractor will be bigger than the rectangle. So you take your pen, 13 degrees is like, that's 10, 11, 12, 13 is like right there. See if I can get it. There it goes. So now you make a little mark with your protractor, right, at the angle that you're looking for. And make sure your protractor is lined up with the normal line. That's important. Otherwise, you're going to have problems making the angle. Then you're going to rotate your protractor so that the edge of it points to that spot that you want the ray to go to. I'm just going to edge it down just a teeny touch like that. And then we extend our ray from that point of contact down towards that angle we want it to go, but I'm not going to pass the second line. I'm going to stop there. Why do I have to stop at the second line? Stop, don't call out, Terrell.
The angle is going to be different when it leaves the diamond.
Bingo, right? Because that's one of the boundaries of the two mediums between the diamond and the air. So at the second boundary, we're going to have a second refraction. There's a refraction once going in, and a second refraction as you leave. Right? Questions so far, anybody? No? Okay. So now we got to do it all over again. Whole thing, right? Because you're doing a second refraction. So first thing we got to do is make a normal line. So when you're at the second point of contact, you put your protractor back at the point of contact, line it up so that the 90 is back on the diamond surface, right, like that. Take a line, make sure it's a dotted line for a normal line, extend it through the surface like so, and then you have your second normal line. Now if you look at it, and if you've done it right, what it's going to look like, it's going to look like you've got two parallel lines, like train tracks. If you've got one line going one way and another line going another way, you're wrong. So don't do that. Great, we've got all that in there. Now, what question? Yeah, absolutely. After I go through one example, because look, all of your values are probably going to be different than what I did, because you're arbitrarily laying this rectangle down. The process I'm using is going to be basically identical. I mean, this is mostly the same setup, except you're just going to change that angle in there. Now, there is one advantage of the fact that it's a rectangle. What do you think is the advantage here?
Ooh.
There's an advantage that this is a rectangle. What do you notice about this line here and this line here? They're parallel to one another. And essentially what you're doing is, you're going here, it's from air to diamond. Here, it's from diamond back to air, right? Now, hang on. This angle on the inside,
It'd be the same angle as
slow, don't pull out. This angle on the inside is, we said, 13 degrees. And because these are parallel lines, what does that make this angle have to be? 13 degrees. They're both 13 degrees. So that tells us this. In here, our theta 2 was 13 degrees. At the bottom, is that our theta 2?
Theta 1.
That's our theta 1. So now, everything is reversed. Instead of n1 being 1, now n1 is equal to 2.42, and our theta 1 is equal to 13. Our n2 is now equal to 1, and our theta 2...
Isn't it the same thing? Wait, isn't it the same thing as what we just, the first one? Yeah, 37.
Exactly. So, the advantage of the fact that this is they're parallel lines means that essentially we don't have to do Snell's law again. Because we don't have to use Snell's law again because you're doing the same thing, but you're doing it in reverse. So while it was 37 degrees up here, it's going to again be 37 degrees down over here, right? So we don't have to redo all the math. because we basically know it's going to be 37 degrees. So I'm going to move everything out of the way.
Did you scan the test?
No, I have not scanned the test yet. So I'm just going to move this stuff out of the way because we don't really need some of it. Just going to move that over there somewhere.
So you said because this is a rectangle, that's why we're able to do this. What if it was like a circle? Then everything would be...
Yeah, okay, so if it's a circle or not a parallel shape, what you would have to do is you would have to do Snell's law again and apply it and measure the incident angle, because in this case our incident angle is equal to the refracted angle from the previous case, and so that allows for it to be reversed. But in a non-parallel interface, what would happen is you'd have different angles of incidence compared to the refracted. So this only works when it's parallel in a prism, rectangular prism, right? If it was a circle or it was like a trapezoid, depending on which part of the trapezoid it's not going to be the exact same. Okay, so now what we do, we take our protractor and it's going to leave now. It's going to leave with an angle of 37 degrees. So we take our pencil, and on our protractor we would mark out that's 35, 36, 37 is like right there. It's not exactly perfect, but it's close enough. Rotate our protractor so it's pointed towards that spot. And then all you really got to do is you've got to just make a new ray that is exiting from that point going down like that. Right?
That's what I was thinking too.
And so,
We're not done.
if we view, no, we're not done, but we're close to done. If you look at it, right, essentially what the prism did, if you did it right, you should see like train tracks for the normal lines, but it also, the beam itself, if you look at the incoming beam and the leaving beam, basically they're parallel. All that the prism did was it took that ray and just shifted it horizontally to the, in this case, to the right-hand side. If you tilt your prism like this, it's going to shift it horizontally to the left-hand side. Right? But we're not quite done because
Why do you have 5 protractors out?
I've got too many protractors. We're not done with the protractor. Here's the problem, right? If I just extend this ray down, right? Just keep it on going straight down, right? It's not going to hit the target. We basically are not going to get what we want. So what we want to do is we want to have a mirror that's going to reflect the ray so that it hits the target. Now where we place that mirror dictates exactly where the reflection is going to be. So what we sort of have to do is we've got to plan out where we want the ray to be before we place the mirror. Yeah, go ahead.
Like, you know how you see it's the new ray is coming down, but it's like a little bit to the right of the target. That if it's going, it can go through the target, right?
No, it can't go through the black spot. The black spot is blocking.
Can it go through the white spot?
No, it's got to hit the black center of the black target.
Okay, so that thing. Okay, because
you have to use a mirror. It's impossible to get it hit the target if you don't use a mirror.
No, that's not what that's not what, like, the black. Never mind. Okay, continue.
Okay. So, what we're going to do for the last part, what you're going to do is you're going to lay out a imaginary line where you want your ray to go. So, I'm going to take a line. I might put like a dotted line to indicate it's imaginary. And just from the point of that ray, I'm going to trace out where I want the new ray to go. Like that, right? So, what is the rule with a mirror? Someone else, I have your. It reflects stuff, sure, that's true.
When the light goes through it, it bends it?
It doesn't bend. It bounces it, right? But specifically, what mathematically happens with a mirror on angles? Kisan. Yeah. Not a different angle.
The same.
The same angle. The rule with mirrors are that when a ray strikes a mirror, it bounces off the mirror with the same angle that it came in at. So for this here, if I want a mirror to be right there, essentially what the mirror is going to do is it's going to split the angle in half. Because we want the same angle going in as the angle that's leaving. So I'll show how that works in just a second. Okay, almost there, almost there. So, what we're going to do is, we're going to split the angle exactly in half. So in order to do that, the first thing we have to do is measure this angle. So I'm going to take my protractor, and what I mean by angle, I mean the angle between the ray, incident ray, and the reflected ray. So I line my protractor up so it's with the incident ray, and at that point of transition, where it bends. And then I measure the angle to where it's going. So in this case, that's going to be 150, 160, 160, I want to say 168 degrees. So our full angle, the full angle, 168 degrees, right? So what we want is half of that. We want to split the angle in half. So half of 168 is going to be 90 and 91, 84, right? Yeah, something. So it's going to be 84 degrees is going to be the half angle, right? So,
Where did you get 34 from?
64 divided by 2.
So,
Wow.
we make a mark at 84 degrees. So this is 90, 80, 84 degrees is going to be like right there. Is that right?
Ew.
No. That's is that right? Yeah, that's 80. Yeah, I got it. Now,
Oh.
shh. Once you mark out the half angle, you're going to do the same thing we did before. We're going to rotate our protractor so it points to the half angle. And I kind of move it over a little bit so I get a nice straight line. Then you're going to create a line that bisects that angle. Cuts it in half. Yes, that's what the bisection is. I was confirming you were correct, Casey. So now you take a line. Now this dotted line that I made represents the normal line for our mirror, right? So our mirror is going to be normal to that line that's bisecting the full angle in half. So all I got to do then,
Just draw a square.
not draw a square, I line my protractor back up at the point of contact. I twist it so that the 90 is resting on that normal line. And then just make sure that it's at the right spot. And then I just draw a line that's tracing down from here to here. I do one. And then you want to do a second one just to indicate it actually has some thickness, this mirror. And then that's basically it.
Whoa.
I have a question.
Question so far?
Yes.
Yes.
Yeah, but I get how you did that, but how are you going to figure out where the mirror is placed? Because
That's
depending
where it
on
is.
the mirror is, you could
This is where the mirror is placed. You don't place the mirror. Like, you don't. Listen. You don't place the mirror first. What you do first is you plan out the path you want, and then the path you want dictates where you place your mirror to meet the conditions of the path you want. Does that make sense? So we put the mirror down after we had already planned out where we want the ray to go. Other questions? Yes.
I got confused when you drew that.
Yeah. You got confused? Okay, all I did was at this spot, I made an imaginary line, a line that I want to go to the target. And then based on that, I said, look, my mirror has to cut the angle between the incoming ray and the outgoing ray in half. Because the rule with mirrors is that whatever angle you have going in has to be the same as whatever angle is going out. And so by cutting that angle in half, I create the normal line of the mirror, because in a mirror, right, the normal line, basically, it's got to go in with the same angle as it leaves. That's just a rule with mirrors.
So all you do is put 90 degrees.
Yeah, I just put a 90 degrees compared to that normal line that's bisecting the full angle. And that 90-degree thing gives us the mirror's location. Wait, one at a time. Yes, Lamel. To help you, right? Okay, I'm going to do individual help. Any other questions before we close out the model on this? Yes?
How does like the laser being shot in a sphere work?
Like I said before, it's going to be different because you're not going to have the same angles at your boundary conditions, right? So a sphere would have like a different angle in as it goes out, and then you have to deal with how big the sphere is and that kind of stuff. Yes?
Sphere.
So if we would have wanted to place the mirror closer to the target or closer to the sphere, the angle will vary, right?
Yes, yes. Depending on where you allow, how far you let this ray go, right? You're going to get a different number than 168. It really all depends on how you draw it. So each person that does it, you're going to have a different answer.
So are we supposed to do the match on the same paper as the...
It would be nice if you could. Any other questions or comments about how to do this?
Okay, so the normal line is just half of the total angle.
Between the incident ray and the reflected ray that you want to hit the target.
Okay, all right.
Okay?
Cool beans. 11.
All right.
Great.
bye.
Okay, I'm going to come around and help you guys do it
Over and
yourself.
out.
Wait,